There is a sound coming from interstellar space, not a metaphor, not an artistic interpretation of data, an actual, measurable, continuous tone vibrating through the plasma between the stars. A hum, steady, narrow in frequency, persisting for years without interruption. And it is coming from a region that every physicist on Earth spent decades insisting was silent. That sound was not supposed to exist. The instrument that detected it weighs 1.4 kilograms. It draws 1.6 watts of power, less than a nightlight. NASA's review board initially rejected it, and it is attached to a spacecraft that was never designed to survive long enough to reach the place where the hum originates. What that instrument found, and what it continues to record, did not simply add a footnote to existing models of our solar system. It forced entire fields of research to start over. There's something scientists don't like talking about in broad terms, not because they're hiding anything, but because acknowledging it requires admitting that everything used to model the space our solar system moves through was built on assumptions that turned out to be wrong. 8 of them, specifically. 8 separate predictions about the structure at the edge of our solar system, each one developed over decades, each one supported by the best physics available at the time. 8 predictions. Every single one of them failed. The boundary between our solar system and interstellar space was supposed to sit roughly 150 astronomical units from the Sun. It was found at 121. The protective bubble around our star was supposed to have a long trailing tail, like a comet. It doesn't. The temperature outside that bubble was predicted to fall between 15,000 and 30,000 degrees Kelvin. The actual measurement came in between 30,000 and 50,000. The magnetic field was supposed to flip dramatically at the boundary, the single clearest indicator that a spacecraft had crossed into interstellar space. When Voyager 1 crossed, the field barely moved. For over a year, no one could agree on whether the crossing had even happened. These are not marginal errors. These are structural failures, the kind that don't get absorbed into a model with a small correction, the kind that require the model to be rebuilt. This is the story of what Voyager found, why it was wrong in exactly the ways that matter most, and what the data from the most distant human-made object in existence tells us about the space our solar system is moving through right now. Hold on to something. Near the end, the implications stop being about spacecraft and start being about what surrounds us on a galactic scale. That part doesn't close cleanly. Voyager 1 launched on September 5th, 1977. The mission's stated objective was straightforward: photograph Jupiter and Saturn, collect whatever science was possible during planetary flybys, then continue outward. Nobody designed it to survive 48 years. The engineering teams who built it did not write contingency plans for interstellar space, because nobody seriously expected the spacecraft to reach it while still transmitting. When the mission launched, personal computers did not yet exist in any commercial form. The code running Voyager's onboard systems was written for processors that have not been manufactured in decades. The documentation for some of that code exists only in archives, and some of those archives are incomplete. Right now, Voyager 1 is approximately 165 astronomical units from Earth. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. At 165 of those units, the spacecraft sits roughly 15.3 billion miles away, and a radio signal traveling at the speed of light takes about 22.5 hours to bridge that distance. When mission engineers at the Jet Propulsion Laboratory send a command, they wait nearly 2 full days to see any result. There is no real-time interaction. Every exchange is a letter sent into space, followed by silence, followed eventually by a reply. Voyager is still listening. Its plasma wave subsystem has been recording a persistent narrowband emission since 2017, a steady tone in interstellar space, roughly 0.04 kilohertz wide, continuous, unconnected to anything the Sun is doing. The hum represents plasma oscillations in the interstellar medium, the thin gas that fills the space between stars. Think of electrons vibrating at low frequencies across enormous volumes of space. The instrument measuring this was never supposed to be the one that mattered. It was a compromise, a backup, an instrument that survived only because its designer agreed to share antenna space with a different experiment to save weight. That instrument became the only tool capable of confirming the most significant boundary crossing in the history of exploration. But to understand why, you need to understand what everyone thought was out there before any spacecraft reached it. Before Voyager, the heliosphere had a settled, well-understood shape. The concept was elegant in its simplicity. Our sun continuously releases a stream of charged particles, protons, electrons, alpha particles, called the solar wind. This wind blows outward in all directions at speeds typically between 300 and 500 kilometers per second. Eventually, far enough from the sun, it runs into resistance, the gas and dust drifting through interstellar space. At some point, the pressure equalizes. The solar wind slows from supersonic to subsonic speed at a boundary called the termination shock. Beyond the termination shock, the solar wind piles up and spreads sideways in a turbulent region called the heliosheath. Think of water from a garden hose hitting a flat wall. The stream spreads out after impact, forming a chaotic layer before sliding off the edges. Beyond the heliosheath lay the final boundary, the heliopause. This was where solar material ends and interstellar material begins. The textbooks were clear. The termination shock would be found at roughly 108 astronomical units. The heliopause would sit at about 150. Beyond it, cold, sparse, featureless interstellar gas at temperatures between 15,000 and 30,000 Kelvin. Quiet, nearly empty. The shape of the entire heliosphere had been decided for 50 years. Because our sun moves through interstellar space at roughly 52,000 miles per hour, the heliosphere was supposed to trail behind like a comet, a blunt, compressed nose on the leading edge, and a long tail extending hundreds of astronomical units in the opposite direction. Every textbook illustration showed this shape. Every model calculated it. Researchers built careers on the comet-tail heliosphere. The magnetic field was equally settled. Our star's magnetic field spirals outward with the solar wind in what physicists call the Parker spiral, first described by Eugene Parker in 1958. At the heliopause, this solar magnetic field was supposed to meet the interstellar magnetic field coming from outside. The collision would produce a dramatic directional change. A compass needle, if you could float one at the boundary, would swing hard. That directional flip was the predicted signature of the crossing, not just a feature the smoking gun that would confirm, unmistakably, that a spacecraft had crossed from the solar domain into interstellar space. Anomalous cosmic rays completed the picture. These particles originate as neutral atoms drifting into the heliosphere from interstellar space. Solar radiation ionizes them, and then they get picked up by the solar wind and carried toward the termination shock, where they bounce back and forth across the shock front, gaining energy with each pass, a process called diffusive shock acceleration. The prediction was firm. When Voyager crossed the termination shock, anomalous cosmic ray intensity would peak. Entire research programs were built around measuring that peak. This was the model: termination shock at 108 astronomical units, heliopause at 150, a clean magnetic flip at the boundary, a cosmic ray peak at the shock, a long tail, cold silence beyond. 50 years of theoretical work, all internally consistent, all mathematically sound, and nearly all of it wrong. The first crack appeared on December 16, 2004, when Voyager 1 had been flying for 27 years. Its instruments registered a sudden change. Solar wind speed dropped, magnetic field intensity jumped, particle counts shifted. The spacecraft had crossed the termination shock the moment heliophysicists had waited decades for. The location: 94.01 astronomical units. The prediction: 108. Voyager hit the boundary 13.99 astronomical units early. That gap, the error in the prediction, is larger than the distance between the Sun and Saturn. The entire model of where the solar wind first encounters resistance from interstellar space was off by a margin wider than the outer planets. The location was wrong. What happened at the boundary was worse. Anomalous cosmic rays were supposed to peak at the termination shock. When Voyager crossed, the intensity didn't spike. It kept rising. Particles continued increasing as the spacecraft moved deeper into the heliosheath, past the shock, pushing toward the heliopause. The termination shock was not the acceleration source. Decades of theoretical work on anomalous cosmic ray acceleration collapsed with a single dataset. The principal investigator for Voyager's low-energy charged particles experiment had built instruments that flew to all 8 planets in our solar system. His detector was the one recording the cosmic ray data as Voyager crossed. The particles his instrument measured were real. Their energies were real, but they were not doing what every model demanded they do at this boundary. The immediate question: where was the acceleration actually happening? Some researchers proposed that anomalous cosmic rays might be accelerated at the flanks of the heliosphere, the sides of the bubble, rather than the nose. Voyager was traveling roughly toward the nose. If the flanks were the real acceleration zone, Voyager would have passed through the shock without seeing the expected peak. This would explain the data, but it created a problem that persists to this day. No spacecraft has ever traveled toward the heliosphere's flanks. No mission is currently planned to do so. As of early 2026, the source of anomalous cosmic ray acceleration is still unidentified. The particles exist, the energies are measured, the acceleration is real. We do not know where it happens. Voyager 2 added another complication 3 years later. On August 30th, 2007, the second probe crossed the termination shock at roughly 83.6 astronomical units, 10 astronomical units closer than Voyager 1's crossing. 10 astronomical units is approximately 930 million miles. The heliosphere was not just smaller than predicted, it was lopsided. 2 crossings of the same boundary at 2 different distances, which meant the bubble wasn't symmetric. Something was pressing harder on one side than the other, compressing the southern flank inward, and the models hadn't accounted for it. 2 crossings, 2 different locations. The first major boundary already wrong in both location and behavior. And Voyager 1 was still more than a decade away from the heliopause, where the real surprises were waiting. There's a detail about Voyager 1 that changes how the entire rest of the investigation unfolds. In 1980, during the Saturn flyby, the spacecraft's plasma science instrument failed. The plasma science experiment, known by the abbreviation PLS, was the primary tool for directly measuring charged particle populations. It could count ions and electrons, measure their speeds, calculate their temperatures. It was the instrument designed specifically to characterize the heliopause crossing. It broke 32 years before the crossing it was built to detect. When Voyager 1 eventually reached the heliopause in 2012, it arrived without its most important sensor. Imagine investigating a crime scene without the ability to collect fingerprints. You can still observe, photograph, measure other things, but the direct evidence you need most is the one thing you cannot collect. This left Donald Gurnet's plasma wave subsystem as the only instrument capable of indirectly measuring plasma density. The device weighs 1.4 kilograms. It draws 1.6 watts. And NASA originally said no. In the early 1970s, when Voyager's instrument suite was being assembled, Gurnet proposed a full plasma wave receiver. The review board rejected it. The spacecraft was already at its weight limit. Gurnet came back with a compromise in 1973. He redesigned his instrument as a compact spectrum analyzer that could share the antennas already allocated to the planetary radio astronomy experiment. Shared antennas, reduced weight, same measurement. NASA accepted. The instrument that would eventually confirm humanity's first crossing into interstellar space almost didn't fly at all. The plasma wave subsystem works differently from the plasma science instrument. PLS directly measures particles. PWS listens for waves specifically, oscillations in the electric field caused by electrons vibrating in the surrounding plasma. The frequency of those oscillations depends on local electron density. Higher density means higher frequency. By measuring frequency, you can calculate density. By calculating density, you can determine whether the spacecraft is surrounded by thin solar wind plasma or denser interstellar plasma. This distinction matters because the heliopause is partly defined by a sharp jump in plasma density. On the solar side, the plasma is thin, dominated by particles blown outward from the sun. On the interstellar side, the plasma is denser, composed of material with no connection to our solar system. If Gurnet's instrument could detect that density jump through frequency measurements, it could confirm the crossing even without PLS. But there was a catch. The plasma wave subsystem can only measure plasma density when something disturbs the plasma enough to trigger detectable oscillations. In calm conditions, there is nothing to measure. The instrument sits silent, waiting for the medium to vibrate. This meant confirmation might not come at the moment of crossing. It might come weeks or months later, whenever a solar event sent a pressure wave rippling outward to reach Voyager's location and shake the local plasma into oscillation. The mission's most critical measurement would depend on a broken primary instrument, a rejected backup that weighed less than a bag of flour, and the cooperation of the interstellar medium itself. Between 2007 and 2008, both Voyagers found something in the heliosheath that nobody expected. The region was supposed to be orderly models, showed the solar magnetic field curving smoothly through it, bending like grain in polished wood as the solar wind decelerated and spread outward after crossing the termination shock. A structured, layered environment where magnetic field direction changed gradually and predictably. What they found instead was magnetic bubbles. Not metaphorical bubbles, actual magnetic structures, each one roughly 1 astronomical unit across the distance from Earth to the Sun. The magnetic field in the outer heliosphere was breaking apart through a process called magnetic reconnection, where field lines snap and reform into closed loops, creating a churning froth of magnetic islands stretching across the entire outer boundary of the solar system. You expected to find a neatly layered cake. Instead, you found a bathtub full of soap bubbles, each one the width of Earth's orbit. This frothy structure had consequences for everything else. Cosmic rays, both the galactic variety coming from outside and the anomalous variety accelerated somewhere within the heliosphere, had to navigate this magnetic obstacle course. The bubbles could trap particles, redirect them, slow them down, or accelerate them in ways no smooth field model could predict. The failure to find the anomalous cosmic ray peak at the termination shock suddenly had a plausible contributing explanation. If the heliosheath was a maze of magnetic islands, the simple model of particles bouncing cleanly back and forth across a uniform shock front was far too naive. The bubbles also raised questions about the heliopause itself. If the solar side of the boundary was a frothy mess rather than a smooth wall, the contact surface between solar and interstellar material might be irregular too. The clean, sharp heliopause of the textbooks was already looking suspect. Voyager 1 spent nearly 8 years crossing the heliosheath. The distance from the termination shock at 94 astronomical units to the heliopause at 121.6 astronomical units was about 27.6 astronomical units, and at Voyager's speed of roughly 38,000 miles per hour. Covering that distance took from December 2004 to August 2012. During those years, the magnetic bubble data accumulated, researchers published, models were revised. But the real test would come at the heliopause itself, where the solar magnetic field meets the interstellar magnetic field and plasma density jumps by an order of magnitude. Every model said that crossing would be unmistakable. The magnetic field direction should swing hard, like a compass needle whipping from north to east. Particle populations should flip solar particles disappearing, galactic particles flooding in. Plasma density should jump sharply. All 3 signatures together would mark the boundary beyond any doubt. Voyager 1 reached that boundary on August 25, 2012. The particle data cooperated. Solar particle counts dropped. Galactic cosmic ray counts surged. But the magnetic field did not swing. It barely shifted. The single most anticipated signature of the heliopause crossing the one scientist had been waiting 35 years to see did not materialize. And because it did not materialize, nobody could agree on what had just happened. On August 25, 2012, Voyager 1 was 121.6 astronomical units from the Sun. The spacecraft had been flying for 35 years. Its radio signal took 17 hours to reach Earth. The data showed 2 clear changes. Galactic cosmic ray intensity jumped to the highest levels in the mission's history, and solar energetic particle counts dropped to near zero. By those indicators alone, Voyager 1 had left the heliosphere. NASA made no announcement, no press conference, no celebration. The reason was the magnetometer. The magnetic field strength had changed slightly at the boundary. The direction had not. Every model of the heliopause predicted that the solar magnetic field and the interstellar magnetic field would point in different directions. The transition between them should produce a measurable swing in field orientation, like walking from a room where all the furniture faces north into a room where everything faces east. you would notice immediately. Voyager's magnetometer noticed almost nothing. The field on both sides of the crossing pointed in essentially the same direction. The project scientist who had led the mission since 1972 could not call the crossing without the magnetic signature. The particle data said Voyager had crossed. The magnetic data said it had not. Without the plasma science instrument dead since 1980, there was no direct plasma measurement to settle the question. This paralysis lasted more than a year. From August 2012 to September 2013, the status of Voyager 1 was officially ambiguous. The most distant human-made object had either entered interstellar space or it had not, and the two sets of instruments on board disagreed. The heliophysics community split down the middle. Two established researchers argued that Voyager had not crossed the heliopause, but had instead entered what they called a depletion region, a zone where solar energetic particles could escape along magnetic field lines, while the field itself remained solar in character. Their model explained the particle drop. It explained the unchanged magnetic field, and it kept the textbook heliopause intact. The argument was internally consistent, but it was also waiting to be contradicted. Donald Gurnett was not arguing. He was waiting for something to vibrate. Throughout 2012 and into early 2013, the plasma around Voyager 1 was quiet. The plasma wave subsystem recorded steady, low-level data. No oscillation events strong enough to calculate electron density. Then, on April 9th, 2013, the medium shook. A coronal mass ejection, a burst of solar plasma launched from the sun months earlier, had finally traveled the 11 billion miles to Voyager's location. When it arrived, it compressed the surrounding plasma and triggered oscillations the PWS could detect. The instrument recorded a plasma frequency between 2 and 3 kilohertz. In thin solar wind, plasma inside the heliosphere, plasma oscillation frequencies sit around 300 Hz. In the denser interstellar medium, the frequency should be much higher. The 2 to 3 kilohertz measurement corresponded to an electron density of roughly 0.08 particles per cubic centimeter, consistent with the predicted density of interstellar space, and an order of magnitude higher than any solar wind density. Gurnett's team published their results. On September 12, 2013, NASA held the press conference. Voyager 1 had entered interstellar space on August 25, 2012. The confirmation came 13 months after the event. From a 1.4 kilogram instrument drawing 1.6 watts of power, an instrument that existed only because its designer had agreed to share antennas 4 decades earlier. The depletion region hypothesis couldn't account for the electron density. The community moved on, but the deeper question remained open. Why hadn't the magnetic field flipped? The leading explanation proposed that the interstellar magnetic field drapes around the heliosphere like a sheet over a basketball, aligning itself along the contact surface. This draping could bring the two fields into rough alignment at the crossing point. It was a reasonable physical mechanism, but no model had predicted it before the crossing. It was constructed after the fact to explain data that the existing models couldn't. This becomes important later. Remember it. Edward Stone joined the Voyager project in 1972, at the age of 26, as its project scientist. He would hold that role for 50 years, stepping down in 2022. In that half-century, he coordinated 11 science teams through encounters with Jupiter, Saturn, Uranus, and Neptune. He served as director of the Jet Propulsion Laboratory from 1991 to 2001, overseeing 24 missions. He was also the principal investigator for the cosmic ray subsystem, the instrument that recorded the anomalous cosmic ray surprise at the termination shock. Stone was the voice that translated plasma density measurements and magnetic field vectors into language the public could understand. When the particle data shifted at the heliopause in 2012, Stone was the one who refused to announce the crossing until the evidence was complete. That caution cost NASA a year of headlines, but protected the mission's scientific credibility. In June of 2024, Edward Stone died. He had heard his spacecraft reach interstellar space. He had watched the 2013 confirmation press conference. He had seen the data from Voyager 2's crossing in 2018. The mission he spent his professional life running was outliving him. Suzanne Dodd took over as Voyager project manager in 2010, 2 years before the heliopause crossing. She led the team through both boundary crossings, through the 2023 communications crisis when Voyager 1 started transmitting gibberish, and through the ongoing instrument shutdowns that are slowly blinding both spacecraft. She is now the person making the hardest decisions in the mission's history: which instruments to turn off, which measurements to sacrifice, which eyes to close permanently as the power supply decays. The scale of Stone's tenure resists easy summary. He joined Voyager the same year as the Watergate break-in. He was still running the project when the first iPhone shipped. The mission spanned the personal computer revolution, the internet age, the smartphone era, and the beginning of commercial spaceflight. Every year, for 50 years, he showed up and managed the data. And his own instrument, the cosmic ray subsystem he built, delivered one of the mission's most disruptive findings: the failure of anomalous cosmic rays to peak where the models predicted. The principal investigator's instrument disproved the principal investigator's field of study. Stone reported the result without commentary. Human continuity matters here because spacecraft do not interpret data. People do. The debates, the decisions about which instruments to keep alive, the arguments between competing interpretations, all of it required human judgment under uncertainty. The data that arrived after the heliopause crossing revealed an interstellar medium that no one had modeled correctly. The temperature of the local interstellar medium was predicted to fall between 15,000 and 30,000 Kelvin. Most estimates clustered around 20,000. Voyager's instruments found temperatures between 30,000 and 50,000 Kelvin. At the high end, the measurement exceeded the maximum prediction by 67%. This sounds alarming until you understand what temperature actually means at these densities. Temperature in physics describes the average speed of particles. In the interstellar medium, the particles are moving fast, which produces a high temperature reading. But there are almost no particles, roughly 1 atom per 10 cubic inches. Compare that to the air in a typical room, which contains approximately 800 billion molecules per cubic inch. The interstellar medium is so empty that even at 50,000 Kelvin, you would freeze in seconds. The particles are fast, but there aren't enough of them to transfer meaningful heat to anything. That distinction matters because it affects how the heliosphere interacts with its surroundings. A hotter interstellar medium exerts more thermal pressure on the heliosphere's boundary. Higher pressure compresses the heliosphere. This is part of why the termination shock and heliopause were both closer than predicted. The outside was pushing harder than anyone calculated. The source of the extra heat points well beyond our solar system. Our star sits inside a structure called the local bubble, a cavity roughly 300 light-years across, carved out by supernova explosions over the past 10 to 20 million years. Those explosions sent shockwaves through the interstellar medium, compressing gas, heating it, leaving behind a hot, low-density environment. The elevated temperatures Voyager measured are not a local anomaly. They are the lingering signature of stars that exploded millions of years before our solar system existed in its current configuration. The boundary of our solar system is shaped by our sun blowing particles outward. It is also shaped by dead stars pressing inward. The heliosphere exists at the intersection of those two forces, and the balance between them determines where the boundaries sit, how thick they are, and whether the bubble we live in is expanding or contracting at any given moment. The 11-year solar cycle causes the sun's output to fluctuate, pushing the heliopause outward during solar maximum and letting it contract during solar minimum. Researchers estimate the boundary shifts by 10 or more astronomical units over a full cycle. The heliosphere breathes, and the temperature of the surrounding medium determines how hard the outside pushes back during each contraction. Voyager measured the outside temperature. It also began measuring density once it crossed the heliopause, and those density measurements would reveal something that still has no explanation, a trend that has been climbing for years and shows no sign of stopping. When Voyager 1 crossed the heliopause on August 25, 2012, it began measuring the density of interstellar plasma through its plasma wave subsystem. The initial readings placed the electron density at roughly 0.055 particles per cubic centimeter. For once, a Voyager measurement landed where theory said it should. Models of the local interstellar medium had predicted densities somewhere between 0.04 and 0.07 particles per cubic centimeter at the heliopause. The number came in inside that window. Scientists exhaled. Then the density started rising. Over the following years, the electron density climbed to 0.12, then to 0.15 particles per cubic centimeter. That is nearly 3 times the initial measurement. Voyager was moving in a straight line through interstellar space at roughly 38,000 miles per hour, and the medium it was passing through kept getting denser. No model predicted this gradient. The interstellar medium was supposed to be roughly uniform. At these scales, density variations were expected only over distances of light years, not the tens of astronomical units Voyager was covering. Starting around 2020, the density increase sharpened. Researchers identified what they called pressure front 2, a region where plasma density jumped by roughly 30% above the already elevated baseline and stayed elevated. As of early 2026, Voyager 1 has been inside this higher density zone for more than 5 years. The front shows no sign of ending. To understand why this is puzzling, consider the distances involved. 1 astronomical unit is about 93 million miles. Voyager 1 has traveled roughly 43 astronomical units since crossing the heliopause. Over that distance, the density has nearly tripled. That is like walking across a football field and finding that the air pressure at the far end zone is 3 times higher than at the near end zone, with no wall or barrier anywhere between. Something is compressing the interstellar medium along Voyager's path, and the source of that compression is unknown. Several hypotheses exist, and none of them have been confirmed. One possibility is that Voyager is approaching a denser region of the local interstellar cloud, a natural variation in the patchy gas between stars. Another is that a pressure wave from a distant source, possibly related to the same supernova remnants that carved out the local bubble, is propagating through the medium, and Voyager happens to be crossing it. A third possibility is that the heliosphere itself is piling up interstellar material at its leading edge the way a boat creates a bow wave in water, and Voyager's trajectory is running alongside that accumulation. None of these fully accounts for the duration and magnitude of the increase. Pressure front 2 has lasted longer than any transient event should at these scales. The data keeps arriving every 45 hours, and the trend keeps defying the models. This connects directly to the persistent hum detected starting in 2017. The hum is a narrowband plasma emission whose frequency correlates with local electron density. As the density rises, the characteristics of the hum shift. Together they reveal that the interstellar medium has structure on scales of tens of astronomical units, with pressure gradients that persist for years without explanation. The medium is not a static backdrop. It is doing something, and we are only measuring it along one narrow line through an enormous volume of space. Voyager 1 spent 6 years as the only human-made object in interstellar space. Then, in 2018, it got company, and what the second probe measured at the boundary did not match what the first had found. The instrument Voyager 2 carried into interstellar space was called the Plasma Science Experiment. It was built at the Massachusetts Institute of Technology under the direction of John Richardson. Its job was direct: point at incoming particles, measure their speed, temperature, and density. Voyager 1 had carried the same instrument once. It broke during the Saturn flyby in 1980, 32 years before the heliopause crossing it was designed to detect. Voyager 2 would not have that problem. On November 5, 2018, Voyager 2 crossed the heliopause at roughly 119 astronomical units from the Sun. Richardson's instrument recorded something definitive. The plasma density around the spacecraft jumped from roughly 0.002 particles per cubic centimeter to 0.039, a 20-fold increase. To put that in physical terms, imagine a room where a single grain of sand floats in a volume the size of a shipping container. Then, you cross a doorway and find 20 grains in the same space. Still almost nothing by earthly standards. But in the diffuse medium between stars, that jump is the equivalent of hitting a wall. The jump confirmed the crossing. Voyager 2 was now the second human-made object in interstellar space, but the details of its crossing did not match what Voyager 1 had experienced 6 years earlier. Voyager 1 had crossed at 121.6 astronomical units. Voyager 2 crossed at 119. The difference, about 2.6 astronomical units, or roughly 240 million miles, sounds small. The two spacecraft were traveling in different directions. Voyager 1 headed roughly toward the nose of the heliosphere, the direction the solar system plows into the interstellar medium, while Voyager 2 traveled at a different angle, southward of the ecliptic plane. Models predicted that both crossings would look fundamentally similar because the heliopause was supposed to be a consistent boundary. It was not. Voyager 1 spent months in a strange transition zone where energetic particles dropped, but the magnetic field refused to change direction. Voyager 2 experienced something cleaner. The boundary was thinner. The plasma transition was sharper. The magnetic field shifted more noticeably, though still not as dramatically as decades of models had demanded. The heliosheath, the turbulent region between the termination shock and the heliopause, was also different for each probe. Voyager 1 traversed roughly 27.6 astronomical units of heliosheath. Voyager 2 crossed about 35.4 astronomical units of it, nearly 8 astronomical units more, roughly 740 million additional miles, through the same region, same boundary. Two fundamentally different experiences. Scientists had expected Voyager 2 to confirm what Voyager 1 had found. Instead, it contradicted it. The heliopause was not a uniform shell wrapped evenly around the sun. It was uneven thicker in some directions, thinner in others, shaped by forces pressing in from outside. Two data points from two different directions painted two different pictures. And with no third spacecraft heading toward the boundary, there was no way to arbitrate between them. The investigation had two witnesses. They disagreed, and the disagreement pointed to something larger than either crossing could explain on its own. The asymmetry had already shown up before Voyager 2 reached interstellar space. It appeared the moment Voyager 2 hit the termination shock. On August 30th, 2007, Voyager 2 crossed the termination shock at roughly 83.6 astronomical units. Voyager 1 had crossed it on December 16th, 2004, at 94.01 astronomical units, a difference of more than 10 astronomical units, roughly 930 million miles. The heliosphere was being squeezed unevenly. On one side, the termination shock sat closer. On the other, it pushed farther out. Something external was pressing harder on the southern flank. The interstellar magnetic field threading through the space between stars was the prime suspect. Measurements from both Voyagers indicated that field was not uniform. It pressed against the heliosphere at an angle, compressing one side more than the other. The bubble our solar system blows into space was lopsided. In 2008, a year after Voyager 2's termination shock crossing, NASA launched a small spacecraft called the Interstellar Boundary Explorer, IBEX. It did not travel to the heliosphere's edge. Instead, it orbited Earth and pointed its detectors outward, catching energetic neutral atoms flying inward from the boundary region. These atoms are created when charged particles from the solar wind exchange electrons with neutral interstellar atoms. They fly in straight lines, unaffected by magnetic fields, carrying information about conditions at the boundary back toward Earth like messages. IBEX found something nobody predicted. Across the sky, there was a narrow ribbon of intense energetic neutral atom emissions. It formed a band stretched across the celestial sphere, roughly circular, cutting through the sky in a configuration no model had produced. No simulation, no theoretical framework, no prior measurement had suggested anything like it would be there. The ribbon's location corresponded to where the interstellar magnetic field was perpendicular to the line of sight from Earth. That correlation was clear. The explanation was not. The IBEX ribbon meant the heliosphere's interaction with the interstellar medium was far more structured than anyone had modeled. The boundary was not a smooth compression zone gradually transitioning from solar to interstellar material. It had features. It had concentrated regions of particle interaction that depended on the geometry of the external magnetic field. The interstellar medium was sculpting our bubble from the outside, and the sculpting was detailed enough to create a visible band of energetic emissions that wrapped around the entire sky. The IBEX ribbon remains unexplained to this day. Multiple theories exist. One suggests the ribbon forms where neutral interstellar atoms are ionized by the solar wind, captured by the interstellar magnetic field, reneutralized, and then sent back toward Earth from a specific geometric configuration. Another proposes that the ribbon traces a region where the interstellar magnetic field drapes around the heliosphere and creates a secondary population of energetic particles. Neither model fully reproduces what Ibex observed. The ribbon generated more questions than it answered, and it pointed directly at a deeper problem. If the heliosphere was not a sphere, then what about the feature every textbook agreed on? What about the tail? For more than 50 years, every diagram of the heliosphere included a tail. It looked like a comet. Our star moves through the interstellar medium, and the solar wind streaming behind it was supposed to stretch into a long wake extending hundreds of astronomical units downwind. The shape was intuitive. It matched fluid dynamics. The front compresses, the back trails. Textbooks printed it. Animations rendered it. The comet-tail heliosphere was one of the most recognizable images in space science, not a contested hypothesis, but settled geometry. In 2017, data from the Cassini spacecraft ended it. Cassini spent 13 years orbiting Saturn. One of its instruments, the ion and neutral camera, was pointed outward toward the heliosphere's boundary, catching energetic neutral atoms of the same type that Ibex was designed to detect. Cassini had a crucial advantage. It observed over a full 11-year solar cycle. That meant it could watch how the boundary responded to changes in solar output over time. When the sun's activity increased, particles at the boundary should respond. The question was how fast that response traveled to different parts of the heliosphere. If there was a long tail, particles from the tail direction would take much longer to respond to solar changes. The signal would have to travel hundreds of astronomical units down the tail before bouncing back as energetic neutral atoms. There would be a measurable delay compared to particles arriving from the nose direction, where the boundary sat closer. The delay would be the tail's fingerprint. There was no delay. Particles from the tail direction responded to solar changes just as fast as particles from the nose. Equal response time from every direction meant equal distance in every direction. No extended tail. The heliosphere was roughly the same size in all directions. Imagine expecting to find a river stretching behind a boat, and instead, discovering the boat is sitting in the middle of a pond. The wake simply wasn't there. Researchers at Boston University proposed an alternative shape using magnetohydrodynamic simulations, something resembling a croissant, with two jets of material extending from the poles of the sun's magnetic field and curling back on themselves. Not a sphere, not a comet, something stranger. Other groups proposed a compact, roughly spherical shape with the interstellar magnetic field imposing asymmetric distortions. The debate remains open. What is not debated is that the tail is gone. 5 decades of textbook illustrations were wrong. Every space agency website, every introductory astronomy course, every documentary about the outer solar system had been depicting a feature that did not exist. One of Cassini's final scientific contributions, made just months before the spacecraft was deliberately destroyed in Saturn's atmosphere in September 2017, was demolishing one of the oldest assumptions in heliophysics. And the loss of the tail had consequences beyond geometry. Without a long, trailing wake dissipating solar wind energy downstream, more pressure had to be accounted for at the boundary itself. The energy that models assumed was bleeding off into a tail was staying close to the heliosphere. The numbers were about to stop adding up. When physicists study a boundary between two different media, one of the first things they check is pressure balance. The pressure pushing outward from inside must roughly equal the pressure pushing inward from outside, or the boundary moves. At the heliopause, outward pressure comes from the solar wind, its embedded magnetic field, and energetic particles. Inward pressure comes from the interstellar plasma, its magnetic field, and whatever else exists in the local interstellar medium. Scientists added up every known source of pressure on both sides. The numbers did not balance. The total measured pressure at the heliosphere's edge was higher than any model predicted. There was more pressure pushing inward than the known components of the interstellar medium could account for. Something was missing from the equation. An unknown pressure source was acting on the boundary, and nobody could identify what it was. This was not a small discrepancy. Ibex's data showed the total pressure at the heliopause was roughly 25 to 50% higher than models produced using all known factors. That is equivalent to an entire additional pressure component the size of the thermal plasma contribution just unaccounted for. Imagine building a dam, calculating the water pressure on one side and the structural resistance on the other, and finding the dam holds firm even though your equations say it should have burst. Something you have not measured is reinforcing the structure. Several hypotheses exist. Some researchers suggest the interstellar magnetic field is stronger than current measurements indicate, providing additional magnetic pressure. Others point to populations of energetic particles in the interstellar medium that current instruments cannot detect. A third possibility involves the structure of the interstellar medium itself, specifically the density rise that Voyager 1 has been recording since crossing the heliopause. Plasma density climbing from 0.055 particles per cubic centimeter to values between 0.12 and 0.15, with a further 30% jump in pressure front 2, adds thermal pressure that older models didn't include because nobody knew it was there. The pressure imbalance connects to every other anomaly. The missing tail means more energy stays near the boundary. The asymmetric shape means pressure is distributed unevenly. The porous heliopause, which the crossings would reveal, means material leaks across the boundary, further complicating the accounting. This is not a situation where one measurement was slightly off. The entire framework for understanding the heliosphere's pressure environment was incomplete. Every boundary condition scientists had used to model the heliosphere relied on assumptions about external pressure that turned out to be wrong. The termination shock was in the wrong place because the external pressure was higher than expected. The heliopause was closer than predicted for the same reason. The shape was wrong because the pressure was not uniform, and now the total pressure budget had a gap that no known component could fill. Something out there in the interstellar medium surrounding our solar system was exerting force that could be measured in its effects, but could not be identified at its source. The textbook version of the heliopause was clean. On one side, solar wind. On the other, interstellar plasma. A sharp line. Cross it and you leave the sun's domain entirely. That was the prediction. Voyager 2's plasma science instrument found something different. As the spacecraft approached and then crossed the heliopause in November 2018, Richardson's instrument detected solar wind particles beyond the boundary. Material from the sun was leaking into interstellar space. The wall had holes. This was not entirely surprising in retrospect. Voyager 1 had hinted at something similar 6 years earlier, though it lacked the instrument to measure it directly. In the months before Voyager 1's confirmed crossing, the spacecraft entered a bizarre transition region that scientists named the magnetic highway. In this zone, energetic solar particles dropped sharply, while galactic cosmic rays surged, but the magnetic field did not change direction. The field lines remained solar in character, connected back to the sun, even as the particles riding those lines were interstellar. Picture a highway running along a national border. The road belongs to one country, but the cars on it come from the other side. The infrastructure is solar. The traffic is interstellar. Particles from outside were streaming inward along magnetic field lines that originated from our star, while solar particles escaped outward along the same paths. The boundary was not a wall. It was something more like a membrane selectively permeable in both directions. Voyager 2's direct plasma measurements confirmed and extended this picture. The transition at the heliopause was not instantaneous. There was a mixing layer where solar and interstellar plasmas coexisted. The boundary had thickness. It had structure. Solar material didn't simply stop at the edge it leaked through, carried along magnetic field lines that draped across the heliopause. The technical term is helioporosity. The boundary allows material to pass through in ways that depend on local magnetic field geometry. Where field lines connect across the boundary, particles flow. Where they don't, the boundary holds. The result is a patchy, inconsistent border that varies from location to location and probably from year to year as the magnetic field configuration shifts with the solar cycle. This porosity has consequences. If solar material leaks outward, it carries energy and momentum with it, affecting the pressure balance at the boundary. If interstellar material leaks inward, it changes the composition of the outer heliosphere. The clean two-fluid model solar wind inside, interstellar plasma outside, was too simple. Reality was a mixed zone where the two media interpenetrated. The porosity also raised a question about protection. The heliosphere shields the inner solar system from a significant fraction of galactic cosmic radiation. If the boundary leaks, that shielding is not absolute. The degree of leakage, how it varies with location and solar cycle, and whether it affects the radiation environment deeper inside the heliosphere, are all open questions. Voyager 2 measured only one point on a boundary that wraps around the entire solar system. With the boundary revealed as porous, the heliosphere as a shape unknown, and the pressure equations unbalanced, the investigation needed something the Voyagers could not provide: a global view, a way to see the entire heliosphere at once, rather than sampling it along two thin lines through an enormous three-dimensional structure. Before that new tool could arrive, the investigation had one more surprise waiting in the data. And it had been there all along, humming quietly since 2017. In the first part of this story, there was a sound, a persistent narrowband plasma emission detected by Voyager 1's plasma wave subsystem beginning in 2017. At the time, it was introduced as an unexplained signal from interstellar space. Now, with the full context of what Voyager has found, that sound becomes something more significant. The emission sits at a frequency corresponding to the local electron density in the interstellar medium, roughly 0.1 particles per cubic centimeter. The bandwidth is narrow, about 0.04 kHz wide. It is continuous. It does not start and stop with solar events. It does not correlate with anything the sun is doing. It is a feature of the interstellar medium itself, a background tone in the space between stars that nobody predicted would exist. Before Voyager crossed the heliopause, the consensus was straightforward. The interstellar medium near our solar system was cold, sparse, and quiet. Models placed the temperature between 15,000 and 30,000 Kelvin. Density was low. The magnetic field was weak. There was no reason to expect activity, structure, or sound. The region was supposed to be the cosmic equivalent of an empty room. Voyager found a concert hall. The plasma temperature measured between 30,000 and 50,000 Kelvin, up to 67% hotter than the upper end of predictions. The density was higher than expected and kept climbing. And the hum was there, persistent, steady, the acoustic signature of a medium that was anything but quiet. Analysis of the hum revealed something deeper. The density fluctuations encoded in the signal followed a pattern called the Kolmogorov turbulence spectrum. This is a specific mathematical relationship between the size of turbulent eddies and their energy, first described by the Soviet mathematician Andrei Kolmogorov in 1941. When a fluid is turbulent, energy cascades from large scales down to small scales in a predictable, measurable way. The interstellar medium near our solar system follows this cascade. It has turbulence on scales of astronomical units, the same unit of distance that measures the gap between Earth and the Sun. Think of it like holding a stethoscope against the wall of a building and hearing the plumbing. You cannot see the pipes. You do not know the layout. But the sound tells you there is a system. There is flow. There is structure. The interstellar hum is Voyager's stethoscope pressed against the medium between stars. And what it hears is not emptiness. It is a fluid in motion, stirred by forces operating on scales far larger than our heliosphere. Those forces almost certainly trace back to ancient supernovae. Our solar system sits inside the local interstellar cloud, which itself occupies a larger structure called the local bubble, a cavity roughly 300 light-years across, carved out by stellar explosions over the past 10 to 20 million years. The heat, the density fluctuations, the turbulence encoded in the hum are all fingerprints of dead stars. Energy deposited millions of years ago, still rippling through the medium surrounding our solar system. The quiet void that scientists expected was never quiet. It was never a void. And the instrument that detected this Don Gurnet's one, 6-watt plasma wave subsystem, had been listening since 1977, waiting 40 years for something worth hearing. In late 2023, that instrument nearly went silent for good, not because it failed, because the spacecraft carrying it started sending gibberish. On a day in November 2023, the data stream from Voyager 1 changed. Where there had been ordered science telemetry, there was now noise repeating patterns of ones and zeros that encoded nothing. The most distant human-made object in existence, 15 billion miles from Earth, was talking. It was no longer making sense. The problem was in the Flight Data Subsystem, or FDS, the spacecraft's central computer. It collects data from all active instruments, packages it into telemetry frames, and sends it to the transmitter for relay back to Earth. Every piece of science Voyager 1 had returned since 1977 passed through this system. The FDS runs on memory chips fabricated in the mid-1970s. Its total memory capacity is 69.63 kilobytes. A single photograph on a modern smartphone uses roughly 3 to 5 megabytes. The FDS has less memory than the text of a short novel. one of those memory chips had failed. Engineers at the Jet Propulsion Laboratory determined that approximately 3% of the FDS memory was corrupted. That sounds minor, but 3% of 69.63 kilobytes is not much room, and the code stored in that region was essential for packaging telemetry. Without it, the FDS could not assemble coherent data frames. Science stopped, engineering telemetry stopped. For 5 months, Voyager 1 transmitted meaningless signals across 15 billion miles of space. The challenge facing the engineering team had no precedent in the history of space exploration. The spacecraft was farther from Earth than any object humans have ever built. A radio signal traveling at the speed of light takes about 22.5 hours to reach it, which means every command requires a 4 or 5 hour round trip before engineers can see the result. There is no real-time interaction, no video feed, no way to directly observe what is happening. Every action is a message sent across the solar system with a day-long wait for any reply. The code they needed to fix was 46 years old. It was written for hardware that no longer exists anywhere on Earth. The documentation where it survived described systems designed by engineers who had long since retired or died. Suzanne Dodd's team had to read through archival code listings, reconstruct the original logic, and figure out how to work around a physical hardware failure in a computer smaller than a modern calculator. From a distance, that light itself needs nearly a full day to cross. Consider what that actually means. You need to repair a machine. The machine is 15 billion miles away. You cannot touch it, see it, or interact with it in real time. The machine was built in 1977. You have portions of the original documentation, but sections are missing. 3% of its processor is physically broken in a way you cannot fix remotely. And if you send the wrong command, you might destroy the machine entirely, and there is no replacement coming. Each exchange is a monologue followed by a day of silence, followed by a reply you did not know you would receive until it arrived. In early 2024, the team designed a diagnostic approach. They would send a single command to Voyager 1 instructing the flight data subsystem to dump its entire memory contents back to Earth, not interpreted data, not packaged telemetry, but the raw contents of every memory address, corrupted or not. On March 3rd, 2024, the command left Earth. It traveled at the speed of light across the inner solar system, past the orbits of Mars, Jupiter, Saturn, Uranus, and Neptune, through the Kuiper belt, across the termination shock, through the heliosheath, past the heliopause, and into interstellar space. 22.5 hours later, it arrived at Voyager 1. The spacecraft complied. 22.5 hours after that, the memory dump arrived at the Deep Space Network antennas in California. Engineers now had a complete map of the damage every memory address, functional or corrupted, laid out in a readable format for the first time. They could see exactly what had failed and what remained intact. The solution was not to repair the broken chip. You cannot fix a semiconductor from 15 billion miles away. Instead, the team decided to move the affected code to other locations in memory where functional chips still had available space. This is roughly equivalent to discovering that one shelf in a library has collapsed, and rather than repairing the shelf, redistributing the books to every other shelf that has room. The challenge was that the relocated code had to work from its new positions. Memory addresses were hard-coded into the software. Subroutines referenced specific locations. Moving the code meant rewriting all the address references so the system could find what it needed in unfamiliar places. Between April 18th and 20th, 2024, the team uploaded the relocated code in small pieces, confirming each segment before sending the next. There was no room for error. A bad command could crash the FDS entirely and end the mission. Every upload required a 4-5 hour confirmation cycle. Every decision was made under the understanding that a mistake could silence the most distant human-made object forever. On April 20th, engineering telemetry returned. The data was clean. The FDS was assembling coherent frames again, routing around the dead chip the way a highway routes around a collapsed bridge. Engineers spent the following weeks verifying each instrument's data stream. On May 19th, 2024, full science data transmission resumed. Voyager 1 was back. The repair took roughly 5 months from the onset of gibberish to the restoration of science. It was performed on a computer with less memory than a modern greeting card, running code written during the Carter administration, from a distance so great that the engineers could not have a real conversation with their own spacecraft. Suzanne Dodd later described the Voyagers as deep space rock stars. The description is accurate, but it understates the fragility. The FDS crisis revealed what everyone already knew, but preferred not to dwell on. Voyager 1 is old. Its hardware is degrading. The corrupted memory chip will not be the last failure, and every year the power situation gets worse. Both Voyager spacecraft run on radioisotope thermoelectric generators, or RTGs. These devices convert heat from decaying plutonium, 2, 3, 8, into electricity through thermocouples. No moving parts, no chemical reactions, just the steady, inevitable decay of radioactive material, producing warmth that gets turned into current. When the Voyagers launched in 1977, each spacecraft's RTGs produced about 470 watts of electrical power, enough to run all 11 scientific instruments, the communication system, the onboard computers, and the heaters that keep fuel lines from freezing. Plutonium, 238, has a half-life of 87.7 years. Every 87.7 years, half the remaining plutonium has decayed, and power output drops accordingly. The decline is roughly 4 watts per year. By early 2026, each spacecraft generates somewhere around 220 watts. That sounds like enough, until you consider that it must power everything. Heaters for fuel lines that would freeze solid and break without them, a transmitter broadcasting across 15 billion miles, computers managing attitude control and data processing, and whatever scientific instruments are still active. 4 watts lost per year means roughly 1 instrument's worth of power disappears every couple of years. Suzanne Dodd and her team face a decision that no other mission management group has confronted in quite this way. They must choose which instruments to shut down permanently. The decisions have already begun. In September 2024, Voyager 2's plasma science experiment was powered down. This was the same instrument that provided the only direct plasma measurements at the heliopause, the device that recorded the 20-fold density jump in November 2018 and confirmed the second human-made heliopause crossing. That capability is now gone permanently. No other spacecraft carries a plasma instrument heading toward interstellar space. That specific type of measurement will not be repeated. In February 2025, Voyager 1's cosmic ray subsystem was turned off. This was Edward Stone's instrument, the one that he served as principal investigator for across the entire duration of the mission. It detected the anomalous cosmic ray surprise at the termination shock in 2004. It measured the surge in galactic cosmic rays that signaled the heliopause crossing in 2012. It is now silent. In March 2025, Voyager 2's low-energy charged particles instrument was shut down. The scientist who built that instrument is the only researcher in history to have constructed instruments that flew to all 8 planets in our solar system. His detector on Voyager 2 no longer sends data. Every one of these shutdowns is permanent. There is no restarting an instrument once the power has been reallocated elsewhere. Each decision eliminates a type of measurement permanently, not just from these missions, but from any mission currently in existence or planned. When an instrument goes dark on a Voyager spacecraft, the measurement it was designed to make disappears from the catalog of things humanity can currently observe from interstellar space. By the end of 2026, each probe will likely carry only 2 or 3 active instruments. The magnetometer and the plasma wave subsystem are the most power-efficient instruments on both spacecraft. They draw the least current and return the most scientifically valuable data relative to their power consumption. They will be the last to go. Engineers estimate they may survive into the early 2030s. After that, there will not be enough power to run any science instrument at all. The spacecraft may continue to transmit a carrier signal for a few more years after that, a radio tone confirming they still exist, drifting through interstellar space, but carrying no data. Then even that will stop. 2 spacecraft will continue moving through the space between stars, intact but mute, carrying golden records that no one will play for millions of years. But before that silence arrived, Voyager 1 had one more trick in its aging hardware. In October 2024, Voyager 1 stopped responding on its primary X-band transmitter. Commands from Earth went unanswered. The Deep Space Network antennas listened and heard nothing on the expected frequency. For a mission that had just survived a 5-month computer crisis, this looked like it might be the end. Then engineers found the signal. It was broadcasting on S-band. S-band is a lower frequency radio channel that Voyager 1 had not used since 198143 years earlier, during the Saturn encounter. After that flyby, the spacecraft had switched to X-band as its primary communications link, because X-band offers higher data rates and better performance over extreme distances. The S-band transmitter was left powered, but dormant, a backup that nobody expected to need again. Something had triggered Voyager 1 to switch back. The exact cause is still under investigation, but the most likely explanation involves the spacecraft's fault protection software. When Voyager detected an anomaly with the X-band system, its onboard logic automatically switched to the backup. The same logic that was written in the 1970s, the same code that engineers had just finished patching around corrupted memory chips, made a decision on its own from 15 billion miles away. It chose to survive. The S-band signal was weak. S-band transmits at lower power and lower frequency than X-band, which means the signal spreads more and arrives at Earth with less energy. The Deep Space Network had to use its largest antennas, the 70-meter dishes, and integrate the signal over longer periods to pull coherent data from the noise. But the data was there. Voyager 1 was talking. It had simply switched to a voice nobody had listened for in 4 decades. Consider what this means in engineering terms. A radio transmitter built in the mid-1970s, installed on a spacecraft that launched in 1977, left unused for 43 years while the spacecraft traveled from Saturn to interstellar space, exposed to the radiation environment of the outer solar system and beyond, powered up and transmitted a coherent signal across 15 billion miles. The engineering margins built into Voyager's hardware in the 1970s are still paying dividends half a century later. Engineers re-established full communication and sent commands to switch Voyager 1 back to X-band. By November 2024, the spacecraft was back on its primary transmitter. The S-band system returned to dormancy, having performed exactly the function it was designed for. 4 decades late, no new science came from the episode. No models were overturned. But it captures something about the Voyager mission that the science alone does not fully convey. These spacecraft were built with margins that their designers could not have imagined would matter. Nobody in 1977 planned for a 4-3-year transmitter dormancy test. Nobody designed fault protection software expecting it to make autonomous decisions from interstellar space. The hardware keeps working, the physics keeps surprising, and somewhere between those two facts, the investigation continues. With instruments shutting down and power fading, what remained to be learned depended entirely on what the last active instruments could still detect, the magnetometer and the plasma wave subsystem. On paper, 2 instruments sounds like the end of an investigation. In practice, these 2 instruments had just delivered a result that overturned one of the last surviving predictions about the heliopause. For decades, models assumed that the solar magnetic field and the interstellar magnetic field would point in different directions. That directional difference was supposed to be the clearest marker of the boundary, the feature that would make the heliopause unmistakable to any instrument capable of measuring field direction. When Voyager 1 crossed the heliopause, the expected shift never appeared. Scientists debated for more than a year about whether the crossing had even occurred. At the time, the missing flip was treated as a puzzle, a local anomaly, something to explain away. It is not a local anomaly. With years of magnetometer data from both probes now accumulated, the picture is unambiguous. The local interstellar magnetic field exceeds 3 nanoteslas, stronger than predicted, and it is closely aligned with the solar magnetic field across the heliopause. The 2 fields, generated by completely different sources separated by billions of miles, point in nearly the same direction. Nobody predicted this. Nobody can fully explain it. 3 nanoteslas is a weak field by everyday standards. A refrigerator magnet produces a field roughly 10 million times stronger, but in the diffuse space between stars, 3 nanoteslas is significant. It means the interstellar medium is exerting more magnetic pressure on the heliosphere than models assumed. And the alignment means the boundary between solar space and interstellar space is not the sharp magnetic discontinuity that 50 years of theory demanded. The boundary is magnetically smooth. That smoothness is exactly why it took a year to confirm Voyager 1 had crossed it. The smoking gun that everyone was looking for, the dramatic field reversal, does not exist because the fields on both sides happen to agree. Whether this alignment is a coincidence of our local galactic neighborhood, or evidence of a deeper physical connection between the solar and interstellar magnetic environments, remains an open question. Some researchers propose that the interstellar field is draping around the heliosphere, aligning itself through pressure interactions at the boundary over long timescales. Others argue the alignment may be specific to the local interstellar cloud, the particular patch of galactic gas our solar system is currently passing through. If that's true, then the alignment is temporary. As our solar system continues moving through the galaxy at 52,000 miles per hour, it will eventually exit this cloud and enter a region where the external magnetic field may point in a completely different direction. The heliopause, when that happens, may look nothing like it does now. The data cannot yet distinguish between these possibilities, but the heliosphere is not sitting inside a random magnetic environment. It is embedded in a field that closely mirrors its own. And the instrument that confirmed the interstellar crossing the plasma wave subsystem that NASA almost rejected in 1973 continues to detect the hum that started in 2017. The hum has not stopped. The density fluctuations have not stabilized. The interstellar medium is still talking, and the last two instruments on each probe are still listening. But Voyager was never designed to map the heliosphere from the outside. It was designed to fly through it. For a global picture, the investigation needed something else entirely. On September 24th, 2025, a Falcon 9 rocket lifted off carrying the Interstellar Mapping and Acceleration Probe. The spacecraft arrived at the first Lagrange point on January 10th, 2026, parking itself roughly 1 million miles from Earth, where the gravitational pull of our planet and our star balance out into a kind of gravitational stillness. On February 1st, 2026, primary science operations began. After nearly 50 years of relying on two probes flying along two thin lines through the heliosphere, the investigation finally gained a tool that could see the whole structure at once. The Interstellar Mapping and Acceleration Probe carries 10 instruments with sensitivity 15 to 35 times greater than its predecessor, the Interstellar Boundary Explorer, which launched in 2008, where IBEX gave scientists a blurry snapshot of energetic neutral atoms streaming back from the heliosphere's edge. The new probe will produce detailed maps with enough resolution to track changes over months instead of years. Energetic neutral atoms are the key. When charged particles from the solar wind collide with neutral atoms in the interstellar medium near the heliosphere's boundary, some of those particles steal an electron, become electrically neutral, and fly in a straight line back toward Earth. By measuring where these atoms come from, how fast they travel, and what species they are, scientists can reconstruct what is happening at the boundary without sending a spacecraft there. Think of it like reconstructing a battle from miles away by listening to the sound alone. You cannot see the field, but what reaches you carries enough information to map the broad shape of what is happening. The Interstellar Boundary Explorer had already proven this technique works. Its biggest discovery was the ribbon, that unexpected band of energetic neutral atom emissions forming a narrow arc across the entire sky that no model had predicted. The ribbon appears to trace where the interstellar magnetic field is perpendicular to our line of sight, but its exact origin remains contested. The new probe will observe the ribbon at far higher resolution and across a wider energy range, potentially resolving whether it originates at the heliopause, beyond it, or through some interaction between the two regions that the lower sensitivity IBEX could not distinguish. But the probe's most important contribution may be something more foundational than solving the ribbon. It will produce the first three-dimensional maps of the heliosphere, or as close to three-dimensional as a single vantage point can achieve. Every conclusion drawn from Voyager data carries the same caveat. Two flight paths through a three-dimensional structure cannot tell you the shape of that structure. It is like drilling two core samples through a mountain and trying to describe the entire mountain from what you pull out of two holes. The probe changes that by collecting energetic neutral atoms from every direction simultaneously, and by tracking how those emissions change as the sun's output varies over its 11-year cycle. The mission can build a global picture of the heliosphere's size, shape, and dynamics in a way that no instrument has ever been positioned to do. The first full sky maps are expected later in 2026. When they arrive, they will either confirm or demolish the competing models that have been arguing with each other since Voyager crossed the boundary. For the first time, the investigation has both a ground-level view from inside interstellar space and an aerial view of the entire structure from near Earth. The question, and it is not a small one, is whether the two views will agree. As of early 2026, we do not know the shape of our own heliosphere. That sentence deserves a moment to settle, not the shape of some distant astrophysical structure observed through telescopes. The shape of the bubble our solar system exists inside. The boundary that separates the sun's influence from the rest of the galaxy. The structure that partially shields every planet in our solar system from galactic cosmic radiation. We have been studying it directly for nearly 50 years, and we cannot draw it accurately on a whiteboard. This is where things stop making sense in the best possible way. The comet-tail model is gone. Cassini ended it in 2017 with neutral atom data showing that particles from the supposed tail direction responded to changes in solar output just as quickly as particles from the nose. No time delay means no extended tail. 50 years of textbook illustrations depicting a long windsock trailing behind our solar system described a feature that does not exist. But what replaced the tail is not settled. A simple sphere does not work either. Voyager 2 crossed the termination shock at 83.6 astronomical units. Voyager 1 crossed it at 94. That 10 astronomical unit difference, roughly a billion miles, proves the heliosphere is being squeezed unevenly. The interstellar magnetic field presses harder on one side than the other. The bubble is not round. In 2016, a team at Boston University proposed a shape nobody had considered. Using magnetohydrodynamic simulations, they argued the heliosphere might resemble a croissant, two lobes of solar magnetic field jutting out from opposite sides while the middle pinches inward. The model is driven by the behavior of the solar magnetic field as it twists and folds in the outer heliosphere, creating two distinct jets of magnetized plasma that curve back on themselves rather than streaming straight outward. The croissant fits some observations. It explains the asymmetry between the two Voyager crossings. It accounts for certain features in the IBEX ribbon data, but it does not match everything. Other groups have proposed shapes closer to a deflated beach ball compressed on one side and bulging on the other, with the interstellar magnetic field imposing the distortion from outside. IBEX revealed that the heliosphere's boundary is tilted roughly 30 degrees from what models assumed, and that the tilt shifts by more than 10 astronomical units as the solar cycle waxes and wanes. The heliosphere breathes. It expands during solar maximum when the sun's output is strongest, and contracts during solar minimum when the wind weakens. A structure inflating and deflating by a billion miles every 11 years. That breathing cycle means the heliopause is not in a fixed location. It is a moving target. Voyager 1 and Voyager 2 each captured a single snapshot of a boundary that shifts constantly. The location each probe crossed tells you where the boundary was on that particular day, in that particular direction, during that particular phase of the solar cycle. Extrapolating from two such snapshots to a permanent three-dimensional shape is exactly the kind of assumption that has been wrong at every step of this investigation. The Interstellar Mapping and Acceleration Probe was built to resolve this. Its sky maps will show the global distribution of energetic neutral atoms at different energies, which corresponds to different distances and processes at the boundary. Over time, as the solar cycle progresses, those maps will reveal how the shape changes. Whether the heliosphere is a croissant, a squashed sphere, or something nobody has proposed yet, depends on data that does not exist until the probe delivers it. We live inside this structure. It shields us from a significant fraction of galactic cosmic radiation. It determines how much of the galaxy's energy reaches the inner planets. And after nearly 50 years of direct exploration, we still cannot draw it. The anomalous cosmic ray problem is now more than 20 years old, and counting. When Voyager 1 crossed the termination shock in December 2004, the single most confident prediction in heliophysics collapsed. Anomalous cosmic rays, particles that originate as neutral atoms drifting into the heliosphere, get ionized by solar radiation, and are then accelerated to enormous energies were supposed to reach peak intensity right at the termination shock. That was the whole model. The shock was the accelerator. Voyager 1 would fly through it and measure the peak. The peak was not there. Anomalous cosmic ray intensity did not spike at the termination shock. It kept rising. As Voyager 1 moved deeper into the heliosheath, the turbulent region between the shock and the heliopause, the instrument designed to detect the peak, the cosmic ray subsystem, recorded a smooth increase with no sign of the expected maximum. Voyager 2 confirmed the same pattern 3 years later. No peak, just a steady climb. Entire research programs had been built on the prediction that the termination shock accelerates anomalous cosmic rays. Doctoral theses, simulation codes, funding proposals. The mechanism seemed so straightforward. Neutral atoms drift in, get ionized, get carried outward by the solar wind, hit the shock, and bounce back and forth across it, gaining energy with each past diffusive shock acceleration. It works for other astrophysical shocks. It was supposed to work here. It did not. The current leading hypothesis is that anomalous cosmic rays are not accelerated at the nose of the heliosphere where both Voyagers crossed. They may be accelerated at the flanks, the sides of the heliosphere where the termination shock curves away from the direction of travel through the galaxy. At the flanks, the geometry of the shock is different. The magnetic field meets it at a different angle. The acceleration conditions may be more favorable there, but no spacecraft has ever visited the heliosphere's flanks. Both Voyagers flew roughly toward the nose. Every direct measurement of the termination shock comes from the front of the structure, not the sides. Imagine investigating a building fire, but being allowed to look only through the front door. You can describe the lobby. You cannot explain what happened in the back rooms. The interstellar mapping and acceleration probe may offer indirect evidence. If anomalous cosmic rays are being accelerated at the flanks, some fraction of the resulting energetic neutral atoms should be visible in the probe's sky maps, arriving from the flank directions. But indirect evidence is not the same as flying through the region and measuring particles directly. The acceleration source for anomalous cosmic rays remains one of the oldest open questions in heliophysics. We know the particles exist. We measure them. We have tracked their intensity across 2 shock crossings, through the heliosheath, and into interstellar space. We still do not know where they get their energy. The termination shock, the structure that was supposed to answer this question, definitively turned out to be the wrong answer. 22 years later, the right answer has not arrived, and the cosmic ray subsystem that first measured the problem on Voyager 1 was powered off in February 2025. The clock on resolving this one just got shorter. If you lined up every unresolved question Voyager has generated and mapped the connections between them, the board would not look like a list of independent puzzles. It would look like a single, deeply tangled case that keeps growing more complicated the more carefully you examine it. Start with pressure front 2. Since roughly 2020, Voyager 1 has been passing through a region of interstellar space where plasma density is 30% higher than the surrounding medium. This elevated density has persisted for more than 5 years. No model predicted it. No definitive explanation exists. Something in the interstellar medium is compressing the plasma along Voyager's path, and the source of that compression is unknown. The front shows no sign of ending. Then there is the magnetic field alignment. The solar magnetic field, generated by our star, and the interstellar magnetic field, generated by galactic processes operating across thousands of light years, should not point in the same direction. They do. Across the heliopause, the 2 fields are closely aligned in ways that no pre-crossing model predicted, and that no post-crossing model has fully explained. Whether this is a local coincidence or evidence of a physical connection between the solar and interstellar magnetic environments is unanswered. The interstellar hum has been continuous since 2017, not tied to any solar event, not pulsed or periodic. A constant low-frequency signal revealing density fluctuations over distances of 10 or more astronomical units. What drives it? Whether it is uniform across the interstellar medium or specific to the path Voyager 1 happens to be traveling, and whether it connects to pressure front 2, are all open questions. The hum and the density rise are almost certainly related. The nature of that relationship has not been established. The anomalous cosmic ray acceleration source predicted at the termination shock, not found there, possibly located at the flanks, unconfirmed after 22 years. An entire category of high-energy particles whose origin we can measure and whose acceleration mechanism we cannot identify. Helioporosity, the finding from Voyager 2's plasma instrument that solar particles leak beyond the heliopause into interstellar space, and that interstellar particles stream inward along solar magnetic field lines. The boundary is not sealed. Material crosses in both directions. How much leaks through, over what area, and what effect this has on the radiation environment deeper inside the heliosphere are all open. A border that leaks is fundamentally different from a border that does not, and the difference matters for understanding how much galactic cosmic radiation reaches the inner planets where life exists. The shape of the heliosphere croissant, deflated sphere, something unnamed, no consensus, and no measurement capable of resolving it until the new probe's sky maps arrive. The two Voyager trajectories provide two lines through an enormous volume. What lies in the directions those lines did not sample remains unmeasured by any spacecraft, and the outer heliosphere pressure imbalance. When researchers add up every known pressure source at the heliosphere's boundary, magnetic pressure, thermal plasma pressure, cosmic ray pressure, ram pressure from the interstellar medium flowing past the total exceeds what models predict. There is an unidentified component pushing on the boundary from outside. The measurements confirm the push. Nothing identifies the pusher. 7 cases, all opened by Voyager data, none closed by Voyager data. The probes were never designed to solve these problems. They were designed to fly past the outer planets and keep going. The fact that they survived long enough to reach interstellar space is an engineering accident that became the most productive accident in the history of space exploration. Productive is not the same as conclusive. Every one of these 7 questions points outward toward a galactic environment that we have barely begun to map. And the 7 questions are not independent. They are threads woven through the same underlying reality, which is that the heliosphere is not what we thought it was. And the space surrounding it is not what we thought that was either. Pull back far enough, and the heliosphere is not floating in empty space. It is embedded inside a structure called the local interstellar cloud, a patch of warm, partially ionized gas, roughly 30 light-years across. Our solar system entered this cloud sometime in the last few thousand to tens of thousands of years, and will exit it eventually. The timing of that exit is uncertain, but current trajectories suggest it could happen within a few thousand years, or it may have already partially occurred. The edge of the local interstellar cloud is not precisely mapped. Beyond the local interstellar cloud sits a much larger structure, the local bubble, a cavity in the interstellar medium, roughly 300 light-years in diameter, carved by a series of supernova explosions over the past 10 to 20 million years. Massive stars in the solar neighborhood exhausted their fuel, detonated, and the blast waves swept the surrounding gas outward, hollowing out a region of unusually low density and elevated temperature. Our solar system sits near the edge of this cavity. The hot interstellar medium that Voyager measured 30,000 to 50,000 Kelvin instead of the predicted 15,000 to 30,000 makes complete sense in this context. The gas outside the heliosphere is not simply interstellar gas. It is gas that has been heated and processed by stellar explosions that happened millions of years before our species existed. The density fluctuations that produce the interstellar hum, the pressure anomalies that nobody can account for, the magnetic field structures that do not match simple models. All of it may be the lingering fingerprint of dead stars' energy deposited millions of years ago, still rippling through the medium surrounding our solar system today. Consider the scale of what that means. A supernova releases roughly as much energy in a few seconds as our star will produce over its entire 10 billion-year lifetime. That energy does not simply vanish. It propagates through the interstellar medium as shock waves, heats the surrounding gas, compresses magnetic field lines, and creates turbulence that persists for millions of years. The Kolmogorov spectrum turbulence that Voyager 1 detects in the interstellar hum density variations following a specific mathematical cascade across astronomical unit scales is consistent with turbulence driven by ancient energetic events and sustained by the ongoing dynamics of the interstellar medium. Voyager is measuring the weather. The weather was set in motion by explosions that predate human civilization by a factor of 1,000. This is not abstract cosmology. The local bubble affects us directly. The density of the interstellar medium outside the heliosphere determines how much pressure pushes inward on the boundary. If our solar system were embedded in a denser region of the galaxy, The heliosphere would be smaller. The termination shock would sit closer to the Sun. More galactic cosmic radiation would penetrate to the inner planets. The size and effectiveness of the heliosphere as a radiation shield is partly determined by our star's output, and partly by the interstellar environment outside, and that environment is the aftermath of supernovae. Some researchers have modeled what happens when a solar system passes through a denser interstellar region. The heliosphere compresses. During periods of dramatically higher external density, it might shrink enough that the heliopause retreats inside the orbit of the outer planets. Galactic cosmic ray flux at Earth would increase. The atmospheric implications are not fully understood, but cosmic ray intensity affects cloud nucleation, atmospheric chemistry, and potentially surface biology over geological timescales. These are speculative extensions, not confirmed findings, but they rest on a foundation that Voyager has made concrete. The heliosphere's size responds to external conditions. Those conditions are not constant over geological time, and our solar system moves through the galaxy continuously, encountering different interstellar environments as it goes. What Voyager detected at the edge of the solar system is not just the edge of the solar system. It is the boundary between our star's influence and the accumulated aftermath of every violent event in our galactic neighborhood for the past 20 million years. The boundary of our solar system is shaped not only by the Sun blowing particles outward, but by dead stars pressing inward. Both forces are real, both are measurable, and the balance between them is what determines whether the bubble we live in is expanding or contracting at any given moment. There is something that does not add up about the two heliopause crossings, and it goes beyond the differences in plasma readings and boundary thickness. Voyager 1 crossed at 121.6 astronomical units in August 2012. Voyager 2 crossed at roughly 119 astronomical units in November 2018. 6 years apart, different directions, different phases of the solar cycle. Voyager 1 crossed during a period approaching solar maximum, when the solar wind is stronger and the heliosphere should push outward further. Voyager 2 crossed closer to solar minimum, when the solar wind weakens and the heliosphere should contract. A weaker solar wind means less outward pressure, which means the boundary should retreat inward. Voyager 2 should have crossed the heliopause significantly closer to the Sun than Voyager 1. It crossed closer by only about 2.6 astronomical units, roughly 240 million miles. Given the difference in solar wind conditions between solar maximum and solar minimum conditions that models estimate, can shift the heliopause by 10 or more astronomical units over a full cycle. The similarity in crossing distances was almost as surprising as the differences in what each probe measured at the boundary. The models predicted a much larger gap. The heliosphere did not produce it. This points to something the Voyager data has been implying throughout. The external environment is not a passive backdrop. It matters as much as what the Sun is doing. The local interstellar magnetic field, measured at more than 3 nanoteslas, exerts continuous pressure on the heliosphere from outside. The thermal pressure of the hot interstellar plasma adds to it. The ram pressure of the interstellar medium flowing past the heliosphere as our solar system moves through the galaxy contributes further. The unidentified pressure component adds more still. The boundary is not set by the Sun alone. It is a negotiation. Think of it like a soap bubble floating in a breeze. The air pressure inside the bubble determines its tendency to expand. The wind outside determines its actual shape and position. If the wind is steady and strong, the bubble holds roughly the same size regardless of small changes in internal pressure. The interstellar medium around our solar system is that wind, and it is not weak. This changes how we think about the heliosphere's stability. If external interstellar pressure is as important as internal solar wind pressure, then the heliosphere's size and shape depend on galactic conditions as much as solar conditions. Our solar system is moving through the galaxy at roughly 52,000 miles per hour. The local interstellar cloud it currently traverses is not uniform. Density varies. Magnetic field strength varies. Temperature varies. As the solar system moves into regions of different interstellar properties, the heliosphere will respond. It could shrink. It could change shape. Its protective effectiveness could change with it. None of this is imminent on human timescales. The current interstellar environment appears relatively stable across the span of recorded history and well beyond. But on astronomical timescales, The heliosphere is not a fixed shield. It is a temporary arrangement between a star and the galaxy it travels through, and Voyager revealed that the galaxy's contribution to that arrangement is louder than anyone had expected. 2 probes, 2 paths through a structure that extends in every direction across hundreds of astronomical units. This is the fundamental limitation of everything Voyager has told us about the heliosphere, and it is worth stating plainly. Voyager 1 flew roughly toward the nose of the heliosphere, the direction the solar system faces as it moves through the interstellar medium. Voyager 2 traveled at a different angle, roughly toward the southern part of the heliosphere. Neither probe sampled the flanks. Neither sampled the poles. Neither went anywhere near the region where the tail was supposed to be, even though the tail's absence was eventually confirmed by a different spacecraft measuring different particles from a completely different location. Every claim about the heliosphere's 3-dimensional structure based on Voyager data is an extrapolation from 2 lines through a volume that spans hundreds of astronomical units in every direction. The interstellar mapping and acceleration probe will provide a 2-dimensional sky projection of the heliosphere, a massive improvement over 2 trajectories, but still a compression of 3 dimensions into 2. To get the true shape unambiguously, you need either many different vantage points simultaneously, or measurements that encode depth information that a sky map cannot provide on its own. The probe's time series data, watching how the heliosphere changes over a full solar cycle, may partially substitute for multiple vantage points. As the heliosphere breathes, different regions advance and retreat, and the resulting changes in energetic neutral atom flux can reveal something about the 3rd dimension indirectly. But indirect reconstruction is not the same as direct measurement. There is a limit to how much geometry you can recover from a projection, however detailed. The most direct way to answer the open questions would be to send a spacecraft to 1,000 astronomical units, far enough to look back and see the entire heliosphere in context, as a single coherent structure against the background of the interstellar medium. This is the interstellar probe concept that has been studied by NASA and the Johns Hopkins Applied Physics Laboratory for years. It would carry modern instruments along a trajectory designed to complement Voyager's paths, sampling the flanks or the polar regions, the places where anomalous cosmic rays might actually be accelerating, where the heliosphere's shape is most uncertain and most consequential. The concept remains unfunded. No mission is in development. No launch date has been proposed or seriously targeted. At current propulsion technology, reaching 1,000 astronomical units would take decades. The fastest outbound spacecraft ever launched New Horizons, which flew past Pluto in 2015, travels at roughly 36,000 miles per hour relative to the Sun. At that speed, 1,000 astronomical units is more than 40 years away. Voyager 1, traveling at roughly 38,000 miles per hour, will reach 200 astronomical units sometime in the late 2030s. That is still less than 1/5 of the distance to the proposed interstellar probe target, and by the time Voyager 1 reaches 200 astronomical units, its instruments will almost certainly be silent. In the meantime, we have what we have: 2 aging probes measuring local conditions along 2 paths through a structure that extends in all directions, 1 new probe measuring global emissions from near Earth, and decades of data that contradict nearly every prediction made before the measurements existed. The heliosphere is the only astrophysical structure we live inside and can study simultaneously from within and at its boundary. No other star system gives us that opportunity, but the opportunity is narrow. It depends on instruments that are losing power and a follow-on mission that has not been funded. We are drawing a continent from 2 footprints and a satellite photo taken from 1,000,000 miles away. The continent is real. The footprints are real, but the map between them is still mostly blank. The power budget on Voyager 1 shows roughly 227 watts available from the radioisotope thermoelectric generators as of early 2026. Voyager 2 is similar. The plutonium, 238 inside each generator, decays at a fixed rate, 4 watts less every year. On a spacecraft where every instrument, every heater, every computer cycle runs on a total power supply smaller than a standard light bulb, 4 watts per year is a countdown with a visible end. The cosmic ray subsystem on Voyager 1 went dark in February 2025, Edward Stone's instrument, the one that discovered the anomalous cosmic ray problem at the termination shock in 2004. that measured the surge in galactic cosmic rays, signaling the heliopause crossing in 2012. It is silent now. On Voyager 2, the low-energy charged particles instrument, built by the only scientist in history to have constructed instruments that flew to all 8 planets, was shut down in March 2025. The plasma science instrument on Voyager 2, John Richardson's device from MIT, the one that made the only direct plasma measurements at the heliopause, was already powered down in September 2024. Each of those shutdowns is permanent. There is no restoration. When the power is reallocated, the capability disappears not just from these spacecraft, but from the entire catalog of active measurements humanity is currently making. By the end of 2026, each probe will likely carry only the magnetometer and the plasma wave subsystem. These 2 instruments draw the least power and return the data most relevant to the open questions that remain: magnetic field measurements, plasma density through wave detection. If the power decline continues at its current rate, these instruments may survive into the early 2030s. After that, there will not be enough power to run any science instrument at all. The spacecraft may transmit a carrier tone for a few additional years, a radio signal confirming existence, carrying no information, and then that too will stop. No other spacecraft is heading toward the heliosphere's boundary. New Horizons is on a trajectory into the outer solar system, but is not expected to reach the heliopause before its own power supply fails. There is no funded successor mission that will cross the termination shock, traverse the heliosheath, or directly sample the heliopause from within. When the Voyagers go silent, in situ measurement of the heliosphere's boundary ends. The interstellar mapping and acceleration probe will continue observing from near Earth, but remote sensing and in situ measurement are not interchangeable. They answer different questions. A sky map cannot tell you the local temperature of the interstellar plasma. A plasma density measurement cannot tell you the global shape of the boundary. We are in the final years of a capability that took 50 years to build and that we have no concrete plan to replace. Every month, the magnetometer and plasma wave subsystem continue to operate. They record measurements from a region of space that no other instrument can currently reach. That data may be the last of its kind for decades, possibly much longer. The central question that opened this investigation was specific. Why does nothing at the edge of our solar system match what we predicted? The termination shock was 14 astronomical units closer than models said. The anomalous cosmic rays did not peak where they were supposed to. The heliosheath was not smooth, but filled with magnetic bubbles the size of the Earth-Sun distance. The heliopause was 20% closer than predicted, and when Voyager 1 crossed it, the magnetic field barely changed direction, leaving the scientific community unable to confirm the crossing for over a year. The interstellar medium turned out to be nearly double the predicted temperature, yet so diffuse that a human body would freeze in it instantaneously. The heliosphere has no tail. Its shape is unknown. Its boundary leaks. A persistent hum vibrates through what was supposed to be silent, empty space. 2 spacecraft crossed the same boundary and described it differently. The magnetic fields on both sides of the heliopause are aligned for reasons nobody has fully explained. An unknown pressure source pushes on the heliosphere from outside. Plasma density along Voyager 1's path has been 30% above the surrounding baseline for 5 years with no identified cause. The source of anomalous cosmic ray acceleration predicted at the termination shock, definitively not found. There remains missing after more than 2 decades of searching. The question is not answered. It has expanded. What started as an investigation into the edge of the solar system became an investigation into the relationship between our star and the galaxy it moves through. The heliosphere is not a fixed shield erected by the solar wind and maintained indefinitely. It is a negotiated boundary shaped equally by what the sun pushes outward and what the interstellar medium presses inward, breathing with the solar cycle, responding to interstellar conditions that shift as the solar system moves through the galaxy at 52,000 miles per hour. The local interstellar cloud, the local bubble, the magnetic field structures left by supernovae that detonated 10 million years ago, all of it presses inward and shapes the bubble we live inside right now. Right now, Voyager 1 is roughly 165 astronomical units from Earth, transmitting data at the speed of light that takes more than 22 hours to arrive. Voyager 2 is about 140 astronomical units out on a different heading, measuring a different slice of interstellar space. The magnetometers on both probes are recording. The plasma wave subsystems are listening. The interstellar hum continues, uninterrupted, coming from a place every textbook once described as silent. The interstellar mapping and acceleration probe has begun scanning the entire sky from its position near Earth, building the global maps that will either validate or dismantle the models that remain standing. Its first full results will arrive within the year. When they do, they will describe a heliosphere that 2 probes spent 50 years crossing and that we still cannot accurately draw. The investigation is not winding down, it is accelerating. The instruments are failing, but the questions are multiplying faster than the power is fading. Every year of new data from both the probes and the mapping mission will sharpen the contradictions or begin to resolve them. Either outcome changes what we think we know about the space between stars. But here is what the Voyager data has not resolved, and what the new probe may begin to reveal in a way nobody has fully prepared for. The heliosphere sits inside the local interstellar cloud. The local interstellar cloud sits inside the local bubble, and the local bubble is not the end of the structure. It sits near the edge of the Orion arm of the Milky Way, surrounded by features superbubbles, stellar nurseries, regions of compressed interstellar gas that we have never measured directly from within a moving solar system. We have observed these features from afar with telescopes. We have never had a probe report back on what it actually feels like to move through them. Voyager has shown us that the medium immediately outside our heliosphere is hotter, denser, more turbulent, and more structured than any model predicted. If that is what the nearby interstellar medium looks like, the region our models were best positioned to predict, the region closest to us, what does that imply about the regions further out? About the boundaries between the local bubble and the denser interstellar medium surrounding it? About the interstellar environment our solar system will enter as it continues its orbit around the galaxy over the next millions of years? The first measurement ever taken outside the solar system revealed that we did not understand the space immediately beyond our own doorstep. The reasonable implication is that we understand even less about what lies further beyond, and that the further out you look, the more the assumptions underlying our models were built on foundations that seemed solid until a spacecraft arrived to test them. Somewhere past 165 astronomical units, in plasma heated by stars that died before the Earth existed, carried on a signal that takes almost a full day to cross the distance between the spacecraft and the antenna waiting for it, the hum goes on. What generates it? What surrounds it? What the first detailed maps of the heliosphere will reveal when they arrive, those are questions with answers still forming. And the answers, when they come, will almost certainly open something larger than what they close. That is where this investigation has always been headed, not toward resolution, toward the next question the data makes impossible to ignore.